you have an icon in the bottom.
So, the gyroscope teslameter. So we think that first of all, obviously, the spinning gyroscope. So we think that obviously this problem has to be with the speed and how the system is going to work with the acceleration. Obviously non-ferromagnetic, because if not, it will not work. Well, maybe, but that's not the thing. And finally, obviously, the magnetic field. So our hypothesis: when a gyroscope made from a conducting but not from magnetic material spins near a magnetic field, it will generate parasite currents. So these currents are going to be called eddy currents, and they are going to be opposed to the rotation of the gyroscope, slowing it down. Okay, so this is our general index, so you can fill this. So our theory, the gyroscope theory, experiment, physical, and mathematical theory, and experimental results, the conclusion and the references. Okay. So the theory, first of all, how do we define a gyroscope? So, well, it's just a plate in a cylinder, normally of steel, passing through it, and that is going to be spinning. In our case, it's the third image. It's going to be spinning horizontally. Okay. Our experimental machines, or devices, if you want to call them. First of all, we use a power supply to make the acceleration, to make it accelerate. A voltmeter to have a better understanding of how our little motor was going to work, that can get our motor to 4,800 revolutions per minute. Our gyroscope made with copper, and finally a robotic clock that we use to get the magnets near the gyroscope. Our physical theory. Well, we thought that obviously the torque is going to have to equal the friction plus the eddy currents. But how do we define the eddy currents? So these are obviously parasite currents, as I said before, and how do they happen? Okay, so obviously we are going to first of all have our gyroscope that is spinning around. Then we can get near a magnet, and the magnet, because it's a moving magnetic field, we're going to have an electric current. And because the electric current is moving, we're going to have these vectors. So these two vectors, as a result of the currents, are going to be opposing. One is going to be opposing, and the other one is going to be increasing the velocity, but the one that at the end matters is the one that is opposing. So, the maths. First of all, with our little motor that we were using to speed the whole entire system, went up until 4,800 RPM. So, how did we measure the difference between the first velocity and our gyroscope? Well, we put them together, and for around 20 seconds each time that we measure this, that it would help the system to get to the maximum velocity. So we got our tangential velocity, and after that, with the equivalence shown in there, we can get the angular velocity of the gyroscope at the moment that we just get the motor out is going to be around 1,500 radians per second. So after that, we thought that it would be a good idea to get the moment of inertia of the whole entire system. So with this little formula, we got the velocity of the disk plus the velocity of the rod per se, and finally the total moment of inertia. So after that, the acceleration of the system. We thought that obviously we are going to have a control example that is going to have friction, and another one with the magnet. So we get these two different accelerations. We get the first acceleration less the other one to get the difference of which the magnet actually works. And finally, we know that this is the general formula of torque, and with this you can get how we got our result of torque. And well, one big thing about this is torque is vectorial, but we were putting to 90 degrees the magnets, so it really didn't matter the sign of theta. Finally, that was our result. Okay. So, our experimental results. First of all, without a magnet, we can see that it's going to last a long time, around 40-something seconds. Okay? It sounds really great and everything, but you can see that the timing was, we were trying to get it good. After this, well, this is just an example video. The clock broke when we were trying to move the whole entire system. So you can see here that it actually works, but it's not how we did it again. But it starts to slow down, and quickly. The other one is going to keep up until 40 seconds, I think, and this one is going to stop at 23. Okay. So, how does the magnet act? This is, I think, a pretty important graph of what happens. First of all, we have our linear way of thinking of the motor without functioning or anything else. So without any magnet, it's going to be linear. But after that, we thought that with one magnet that we were using, we could get control results, and after that, a second magnet. If you can see there, the 16 volts, what is not present in 1 and 2 magnets. That is because our tendency line is from, I think, 3 to 4 seconds of space. So it was giving us times up until a minute and 3 seconds or 51 seconds, okay? So we thought that the magnet's position could vary, or it could be a pretty interesting thing to see it changing. But we thought, first of all, what if we put both magnets north and north, and north and south, like you can see in the images, and expect a different result. We thought that this would affect the phenomenon, but it didn't in any way. Still, we tried on with these types of experimentation, but we didn't find anything new about this. With 0 degrees, putting them in parallel, I think it's set. The time would be 18 seconds, but in 45 degrees, it's around the same time, 1 second mostly, without any change. After that, we thought, well, maybe at 90 degrees would happen something, but it did not matter. And finally, at 180 degrees, it actually does not affect the phenomenon. Okay, so I think that this is pretty important to have in mind. And well, I just remembered something. When this type of system is going to work without any noise, and it's just going to heat up a little bit of the moving copper disc. So, well, the faster the wheel is going to spin, the bigger the effect is going to be, meaning that as the wheel is slowing down, so will the eddy currents are going to slow down. These will give us a kind of smooth braking. You can see this in the roller coasters, and I think the Shinkansen train. After that, this also means that the eddy current is unusable at low speeds. It's like a second point and an inference of what you get. And finally, this kind of brake does not have any mechanical contract, so it's not going to make odor or sound. And finally, the angle between the position of the magnet is not relevant as we observed. We thought that this was going to affect or something else, but it's not important. So here are the references and some extra things that I would like to say. This is our power dissipation. And the applications. You can see here that it actually works in the real world. Okay. And some are tables of results.
Thank you very much. Now we have time for questions from the opponent.
First, I'd like to thank you for your presentation. My first question is, do you have any quantitative prediction on the torque from the magnetic braking?
Oh, quantitative
So
predictions.
if I were to give you like essentially the field strength and the geometry of the disc and moment of inertia, would you be able to generate like a velocity time curve?
Yep. Would you agree?
Like, it's a short answer, yes or no?
Yes.
If you can't, so given the field strength, you can generate that curve.
No, this one is not going to work with
This is empirically determined, right? Is this empirically measured, or is your curve later on theoretically predicted?
Oh no, this is practically.
Oh, I see. Yes. So the problem statement says gyroscope, which implies fixed at one point, and which also implies that the gyroscope may go into precession. Do you think by fixing your gyroscope on both ends, you're able to observe the correct phenomena?
Yeah, I think that we can observe the correct phenomena
Also, how did you produce a magnetic field?
with the production of the magnetic
Yes.
field of the eddy currents.
Was it permanent magnet or electromagnet?
Oh, it was a permanent
So
magnet.
you were not able to vary the field strength, correct?
No, yeah, we did because we used 1 and 2 magnets.
So you varied the number of them. So you said your magnet slows down. So does your system lose energy over time?
Yeah, it happens.
And where does it lose its energy?
Oh, the friction. You can see this on the moment of.
So is it heat?
No. Well, yes, but
If it's heat, did you measure the temperature change of your disc?
no.
Also, did you measure the drag of your bearings without an actual electromagnet on it?
Yeah.
Or magnetic field applied?
Without a magnetic field applied, just the gyroscope is spinning.
Yeah.
Okay. Yes. So pass it to. We have it here. It's on the graph.
Correct. And also, what was the thickness of your disc?
The thickness of our disc was 3 millimeters. No, it's not 1.
And
Thank you very much. Yeah, your time is up, and now we have time for preparation.
derived from this problem statement is to first construct a controlled experiment to vary the relevant parameters, including the field strength, the position of the magnet, and the potential of the material for this. The second task will be to consider relevant literature to derive an expression for potentially the magnetic braking torque that comes from these eddy currents. And then you may want to expand the current literature to account for more limited cases such as thicker disks and faster speeds. And finally, you would want to verify your theoretical model by testing the relevant parameters that I described. So first, the summary of the report. They included the relevant theory, including a qualitative explanation of eddy currents, and a quantitative empirical model for the torque, but no actual prediction for the torque of the magnetic field. Then they introduced their experiments with motors to speed up the disk and how they produce a magnetic field with the magnet. And then they went into their experimental results and what trend lines they were able to get from their experiment. So here are some merits and next steps of the report. So I believe they had a good qualitative explanation of how energy is lost in this system and the production of eddy currents from the spin of the disk. And they had interesting discussion of the magnet's position, including with the variation of the number of magnets applied. However, I believe there are a lot of possible next steps for this report, including firstly that there is no quantitative prediction given like the relevant parameters such as the field strength and the material of the disk and its geometry. And there is also a lack of consideration for the precession of the gyroscope. So because it's fixed at two ends, they may have missed out on some parts of this phenomenon that I'd like to discuss later in the discussion. In addition, they have not stated their assumptions that they have made when they were doing their empirical model for torque. And I believe this could be expanded upon in discussion as it includes a thin disk and a slow angular velocity, which is an assumption clearly broken in their experiment. Second, there's a limited control of their experimental setup, as they were not able to vary the field strength material, and they also did not empirically determine their bearing drag separate from their magnetic braking. And I believe this is very important, as currently the assumption is that the drag from the bearings is a constant. However, we believe it is dependent on the angular velocity of the disk itself. So, an overview of my discussion. So first, I'd like to go over some potential quantitative models for how to for the magnetic braking torque. Then I would like to suggest some improvements on this theoretical prediction that we did in part 1. Finally, I would like to suggest some experimental improvements on how they may be able to vary relevant parameters and how they may be able to more accurately measure the deceleration of the disk. So I'd like to go into the discussion. So, in your presentation, I asked you during the question and answer period that you had a theoretical model to predict the torque, right? So, can you expand? Do you have one of these?
Yeah, I do not have one, but this one is going to be practical.
Oh, so it's empirically determined. Mm-hmm. So, if I were to ask you, how would you go about deriving a potentially like theoretical prediction for this?
Okay, so first of all, you should know the magnet's force. Yeah.
So if I were to ask you like, to determine the torque essentially from like the magnetic braking as like a function of like your magnetic field strength, your disk diameter and its angular velocity, how would you go about doing this?
Okay, for sure. So first of all, we know that the magnets are going to be working right now, and I'm thinking right now. So basically, what will happen would be that the velocity would affect the magnetic field, because it is a movement of a non-ferromagnetic material. Okay, so there would be currents around it, and these currents, because they are in movement, they are going to produce.
Right. So this is a qualitative. Sorry, this is like a qualitative explanation, right? So perhaps what you might want to do is like first start with drawing the geometry. Is your magnet cylindrical?
Yeah, it's cylindrical.
Yeah. So if it's cylindrical, can you draw the eddy currents on this? So if your magnetic field is going into the page here, and your disk is spinning about this axis here, can you draw and glue your eddy currents?
For sure. So obviously in my presentation I put them like this, but they would actually go around.
Why would they go in this? Can you draw your directions?
For sure. Okay. So, yeah, because this is in movement, we know for sure that this is going to be stable. Okay, and the electricity passing through these.
So this would be the induced current. Yes.
Okay, and this is going to affect the movement.
So perhaps, like I understand what you're trying to do, but I believe this is still qualitative. So perhaps you may want to use Ohm's law, which states that your induced current density is equal to your your resistivity times your electric field plus your Lorentz force, essentially your V cross V. Perhaps this may lead you to induced current density along your whole field.
Yes, sorry. Okay. So this for sure would help a lot because you can get, because you have this variable, you can get the total velocity, the total electricity of the velocity.
So do you think this is viable? Do you think this would lead to some prediction?
Might be. I would have to.
So then from your induced current density, which would be like actually a function of the x and y position, from here, where would you go to divide by the breaking point?
Okay, so sorry, could you repeat your point, please?
So like from your induced current density and your magnetic field in a localized area, what would be the force acting on this?
The force acting on this disk, well, obviously you first have to get this. You would have to start explaining. Can we move?
Sure, I can go to that. So like your force on the disk would definitely point this way, right?
Yeah.
Right, because that's decelerating, right? And it would be equal to J. And the magnitude of this cross your E field. Because it's essentially your current density times, like your current induced times your magnetic field, which is your force, right? And for your force, you can easily go to the torque, right?
Yeah. I was trying to.
Do you think this would lead to some theoretical prediction for that?
So yeah, for sure, because you're having the quantity of the magnet that is going to be affecting the system, and you have the exact position on where the force is going to affect.
Right. So perhaps you may want it to have done something like this too. Like rather than just fitting curves to your data, you might have wanted to generate a theoretical prediction. Right. Then from this you can get your breaking point. So moving on to another point. So this is right now currently what's done in literature as of like around 2000. A paper published in 2000.
Yeah.
So
I think I found it, but
so some potential improvements on this. So like if I were to do like, so right now this assumes a thin disk, which essentially means that in the z direction pointing in, there's the induced current density is 0, which means it's all planar, right? But if I were to ask you, right, if you have a thicker disk, right, and your magnetic field is like, so this is looking from the side, right?
you're thinking about the skin effect,
Right.
Okay. So you would have the electric currents right here, and it will not pass all the barrier of electrons, right?
Right. And so what would be the relationship if I were to do like if this is your z direction, if your magnetic field is coming down, this is your positive z direction, what would be like your induced current density as a function of z? Can you just sketch us something?
I think, well, obviously,
At a constant angular velocity.
okay. So it would go low. Okay. So because it's a no. It would get stagnant at some point.
Yes, stagnant. So you believe it will increase and then asymptote towards something. I actually disagree with you. I believe the induced current density will actually decrease like that, exponentially, because we know at a constant angular velocity, the magnetic field's permeability depends on an angular velocity, which exponentially to a thicker material.
Oh, and it's because you said that it would be an constant angular
Right,
velocity.
Right, but then at like a fast enough speed, well, any speed really, it would decay exponentially, given a phase. So
Okay.
this,
It's for the thickness.
right. So potentially this is like adding novelty to like a report, for example, because this would be going beyond what's already in literature. Also, now moving on to your experimental setup.
Okay.
So if I were to draw like it, so right now, as far as I understand, your experimental setup consists of the rod, right?
The rod, and we have some bearings right here.
Oh, you have there.
Yeah. So it's not actually fixed to the system, and it's actually. Could I draw?
Right.
The best example of what is actually happening? You have the bearings right here, and it's passing through it. So you have your gyroscope, and you have these two bearings right now that are working to lessen the friction of the whole entire system.
Right. And did you measure the friction just from the bearing?
Just from our bearings, I think that we did not, but we got the angular velocity with the bearings.
Like without a magnet.
Without a magnet.
Like what percentage of deceleration is from the bearings compared to the magnet?
Around
your torque from the bearings over your torque from your magnet. Can you give me approximate percentage?
the torque from. Yeah, I think that I would. It's around maybe double. No, maybe around double.
So your magnetic braking torque is actually less than the inherent torque.
Sorry, I confused. I thought the magnetic without the magnetic field, we would have less friction, obviously, if you want to call it like that, and it would stop at double the amount of time. Like if you can see there, right there.
Double the amount of time. So that would lead it to like 1 over root 2.
Yeah, 1/2.
So for this, so right now your bearings drag make up a large portion of the total dragging of system. So perhaps an improvement to this would actually be to, rather than using bearings, you may want to actually take your plates and mount them vertically and just make a small divot in the top and bottom, and then mount your disc essentially on a point on both sides.
Oh, we tried that actually. We don't have images, but because of the nature of how we were spinning up our gyroscope with a little point of contact here, and after a lot of contacts between the little motor that we were using and the contact point, this spot started to get out.
Right. So perhaps adding some oil to increase the viscous friction here would make this more viable for an experiment. Because if you're trying to determine the magnetic braking torque, it's best to reduce your drag from bearings as much as possible, so you're able to reproduce the phenomenon to its fullest. Thanks.
Thank you very much. And now we have time for opponent to summarize the discussion.
So I believe in our discussion we went over quite a few points. First, potential way to model the magnetic braking torque of the system from literature, and some potential ways to improve upon what's already done in literature. And I believe if we had this, it would be much better. We also went over some cases in which you have a thicker disk and a faster angular velocity, in which your magnetic field would not fully permeate your disk. And finally, we went through some experimental improvements in which they can possibly reduce the drag from their bearings by using some oil on the top and bottom and mounting your disc on a point rather than a bearing. That's what I'll be discussing next.
Thank you very much. And now we have time for questions from the viewers.
Okay. Dear reporter, didn't you try to vary the magnetic field by increasing the amount of magnets? Yes or no?
Sorry, could you repeat?
Did you try to vary the magnetic field strength?
Oh yeah, for sure.
Okay, thank you. How the deceleration coefficient will change if we will take alternating magnetic field instead of constant one?
Okay.
Short answer, please. Increase or decrease?
I think it would in an alternating magnetic field.
Yes.
I think it would decrease.
Okay, thank you. And that one, in the alternating magnetic field, will the deceleration coefficient will be higher or lower than in constant one?
In an alternating magnetic
Yes,
field,
yes.
I believe the deceleration is sine squared.
Okay, thank you. Dear reporter, how did you, could you briefly explain what causes the eddy currents in your system?
The eddy currents in my system?
What causes those currents?
Oh, the magnetic field that has the moment.
Okay, thank you. Dear opponent, could you explain what causes the eddy currents in those systems?
By Lenz's law, the eddy currents are induced by the changing
Okay,
magnetic field.
thank you very much. Dear opponent, how do you assume, or how do you think, if you will take a ferromagnetic disk, will we observe this phenomenon?
The phenomenon will be much reduced as after like a few rotations, the magnetic dipole moment of the disk will be aligned with the magnetic.
Will we observe
applied
this
magnetic
phenomenon, yes or no?
pardon?
If we will take a ferromagnetic disk, will we observe those phenomena, yes or no?
It will decelerate in the beginning and it will asymptote
Okay,
towards
thank
a
you.
constant angle.
Dear reporter, if we'll take a ferromagnetic disk, will we observe the same phenomenon as with the copper one?
If you have it to not stick to the
If,
disk,
for example, we'll take a ferrum disk instead of copper one.
okay, the magnet will stick, or
Will we observe those
yeah,
phenomena?
we can.
Okay, thank you. Dear reporter, did you try to estimate the friction in your system?
Yeah.
Yes?
Like the.
Did you estimate
storage.
the function of friction? Okay, thank you. Dear opponent, what are the energy dissipations in this system?
The eddy currents, which create a braking torque, primarily dissipate energy as heat.
Okay, thank you. Dear reporter, is that all energy dissipations in your system?
Yeah, it's energy dissipation.
Okay, thank you. Did you try to vary the material of your disk and its thickness?
The thickness, no, we couldn't get another copper
Okay,
disk.
thank you.
Thank you very much. Now we have time for you to put the answer.
Sorry, can I?
Yes.
And now we have time for review.
Yeah, okay. My dear ladies and gentlemen, my name is Kalesnikau. I'm the review of Belarus, and I'll represent my review to the London Gyroscope Teslameter. And for first, let's do some summary of the reporter's test. So, qualitatively, he explained those phenomena as that here appears some eddy currents which decelerates the disk, but the main disadvantage of the quality description was that the reporter didn't didn't explain the nature of those currents. So he didn't explain why they appear. And it is a major disadvantage because it doesn't allow us to understand those phenomena more deeply. The third model was explained as introducing some deceleration coefficient, and by varying the parameters of the system, he looked for a change in those deceleration coefficient. I think it's quite good, but the main disadvantage of the theory, as was admitted by the opponent, is that it doesn't predict this phenomena quantitatively. And also the major disadvantage of those reports was the experimental stuff. So during all the reports we've seen only one plot, which was explained quite poorly. So he said just that when we add magnetic fields, our deceleration coefficient changes, and there wasn't explained the type of those dependence and how it will change on the other relevant parameters, and there was only a few, only a lack of experimental data. So also the motion of the disk can be controlled in a low range. So he changed only the position of the magnets and the distance between the axle and the magnets. And also he said during my qualifying questions, he said that he didn't calculate the friction coefficient, and I think it's a really major disadvantage because there could be a very those dependencies will have a really significant influence. It will also create an additional deceleration moment. It could depend on the velocity of our disk, and also it could contain some constant moment of friction, which will also decelerate error, and it will complete his theory. So now let's move on to a position summary. So the speech of the opponent was quite good. So qualifying questions were really apt, and they were all of them were relevant. And the summary of the report also was quite good, except one point. The opponent just agreed with the reporter that there will appear some eddy currents, but again, the nature of those currents wasn't explained. And during all the discussion, the reporter just touched mathematical aspects of those phenomena. He tried to derive the deceleration force, which I think isn't good for this problem. And also the deep understanding of problem was shown in a discussion, but the main disadvantage of the discussion was that the opponent discussed only his own solution to the problem. So he spent most of his time by deriving many formulas, which aren't really significant for those cases, because the solution of the reporter was consisted of the investigation of deceleration coefficients, but not on the formulas themselves. And there were only a lack of opinions. As I said before, in discussion there was only a few points with many math, and it wasn't explained from the physical aspect.
Thank you very much. Thank you very much. Now we have time for a reporter to have a conclusion remarks.
Okay. So, well, first of all, I was going to answer one of the main points. The energy dissipation does not only happen with heat, it too happens with a little bit of sound, because as you can see in the videos presented before, there's sound, there's actual sound. And, well, the friction when we put vertically our gyroscope, what would happen normally, it would make a drill effect after time. After testing, after every test that you would make, it would start to affect this part, because you have the gravity affecting you. And finally, the friction, I think that it was constant for the bearings. We tried to keep it as normal as we could, if you want to say it.
Okay, thank you very much. And now we have time for Joy to ask questions. If there are any.
viscous friction on the disc with the air. So the viscous friction doesn't depend at orientation of disc at all, but dry friction depends on the normal reacting force.
That's
So-
great, thank you. To the component, other than the friction itself, is there any difference between the vertical and the horizontal?
There's no main difference in the friction itself, but the reason I suggested this in the discussion is so that after you get this thing rotating around its axis, you can actually just lift the top plate and you can observe the gyroscope.
I'd like to ask a comment. You were asked what will happen if the magnetic field will alter it, and just didn't hear your answer. Would you please just repeat
So
what you
actually
said?
mixed up the understanding of the question during the answer period as well. So
Can you also say what you said and then what
right.
how did
So
you
during the
change
answer period, I suggested that the torque would be sinusoidal. I still agree with that, but
Torque will be?
sinusoidal.
Oh, okay.
Right, but to expand on that, I believe the torque, the average torque will actually increase due to the changing flux in the magnetic field.
I was wondering what.
Sure. Yeah.
Can the recorder go to slide 17? Can you go to slide 17? Where you have the angular acceleration. Yeah, that very first equation there. Can you talk to us, is your angular acceleration or deceleration rather constant, or do you think it varies as the wheel slows down? And what have you assumed here?
We assumed it was constant. It might have varied a little bit, but we thought it would be good to have an average.
And about the experiment, how did you make sure that magnet did not touch the disc?
Oh, we have a little claw that we couldn't show it in the video because it's broken. It would move only like this, and we have the gyroscope mounted on it, and it would go down with the magnet.
So you are moving the gyroscope and the magnet is fixed.
No.
The other way around.
You're moving the magnet and the
Uh-huh.
gyroscope. And you do all the experiments like that, only the video was
It broke down, and we finished the averages of the graph with it. I think it was the last, the second magnet one. We did it with the hands.
Right. And how did you make sure that it didn't touch if you do it with the hand?
Oh, it was.
Because I think you did it the video, right? So I assume that wasn't the experiment actually. They're free to speak as well.
I just, okay, I'm just taking the word here for a second. Actually, what we were doing is just to rely like a principle, a cloud on the table. So we were just like, when it's time to push the magnet down, we were just pushing it down. Like we were already positioning the magnet before doing it, so we were always getting the same, well, the same distance from the disc.
Right. Any more questions?
I have no questions this time.
Yeah.
Well, I guess I'm going to ask.
Yeah.
You're going to make me ask
Avoid
questions.
that.
So your second question when you were questioning the recorder, you talked about this requirement for gyroscope to have a free end. I actually Googled that while you guys were talking to make sure that was actually a requirement of a gyroscope. Unfortunately, you spent so much time in theory, you didn't get to it. How do you think making a free end would actually affect your results?
Right. So I believe so if the gyroscope were to go into a precession, its velocity vector would essentially change direction, and like an alternating magnetic field, the oscillating velocity vector would also create an oscillating torque on the whole disk. So your angular acceleration would no longer be like simple proportional to the angular velocity, rather it would be like sinusoidal to the like sinusoidal factor times the angular velocity.
Thank you.
Thank you very much. Now we'll try to decide the grades. Hello.
Sit down.
have our grades ready. We will do the same thing than last time. We'll start from the further end, and we will start from the torches. And we got 3, 3, 3, 4, 3. Then for opponent, it's 5, 9, 6, 6, 8. And for viewer, we have 7, 5, 7, 8, and 6. Okay, so we can start with a report. We had 3 and 4. So whoever would like to speak, that would be very appreciated. Maybe 4, you kind of have
All right,
to.
yeah, sure. So it's clear you realize, I hope you realize now, what the fundamental flaw of your report was. What you're going to see as you work through this week, every one of these reports is going to have some predictive model that they then compare the results to. So when you basically take data and just look at the data that you've collected and say, see this, we observed this happening. That doesn't really get to the root of what IYPT is. Now this is a learning experience for you, so you're going to pay attention to that as you go through the week. However, what I will say is, and the reason why I think I'm more elevated than everyone else here, part of the opposition's questions, I think, were unfair in attempting to get you to derive a formula that they were familiar with. And I gave you some amount of credit for really trying to have a productive discussion in this way. You were trying to give them what they wanted, and so at least in my case, that elevated your discussion score. But a 4 is still really low. Still relatively low.
I actually did not subtract the points because the opponent was trying. I think for me it was your chance to get extra points because opponent was trying to help you. So don't feel like just because you didn't know this equation. In my eyes, you didn't get less points. Yeah, I take like what is on your presentation, and then if you would add something in the discussion, it would be only plus. It was nice. But I also appreciate that you wanted to try something new, wanted to try the different positions of the magnet. But as I understood it, it was like we tried some positions, and we did not expect that anything will change, and anything was changing. So that's a very difficult situation to kind of show and prove. It would be more interesting if you think about the situation when something happens, you predict what will happen, and then you confirm it with the experiment. So if you add maybe more magnets instead of just, changing, just one part maybe, so try to surprise, kind of like confirm your thoughts rather than just, yeah. Any more thoughts about the, yeah, and then for the opponent, we were not too consistent, but that's fine. You see different opinions about what we would like to see as the opponential. Because there was 1-5, yeah?
In my opinion, the situation is the same as in the previous stage. The reporter hadn't any explanation for the phenomenon. In this situation, you need, or maybe you must, to discuss all the basic physics and to help him to understand some details of the explanation. But you go higher and don't help him.
Yeah, I think I can add something to that. I think Professor said that if you go too high, is that you direct that part, the second part is not derived from a very simple physical picture. Okay, you just written down B cross B. So what's the B stand for? For the disco, for the electron inside the disco, or for the areas, something like that. You didn't say, you didn't making any explanation about that. Just written it down. So I don't think that's really helpful. Although you are trying to express what you want to proceed, but since in this way you didn't go far. You just make things not really clear. That's my
Yeah, from my perspective, I didn't think that it was your role to explain your theory to someone else. You made it clear what you think about the problem. I really appreciate the way how you discuss. You tried to engage the reporter as much as you could, and you just, discuss physics. I think it was very useful to bring a new insight about the problem. I think what you were talking about was very, very relevant. You have very good points. You did not say, no, you're wrong. You kind of lead to the answer. You were trying to explain your reasoning for why you're saying what you're saying, and I really appreciate it. And I have more points.
Yeah, I mean, I was the highest mark, and I thought, given the presentation, that was exactly what you should have done.
Yeah.
Right? Like, you tried to go back to fundamental physics. Maybe you could have, gone even further back and talked about concepts, but I also thought you did quite a good job of gauging. So you started by saying, okay, can we derive from this law? And then when you clearly didn't understand, so well, imagine that the talk was in these was sort of a function. What are the relationships? And then when he didn't sort of bite, you said, okay, draw me the eddy currents. So I thought you did a good job of trying to get to a level where you could have debate. And I think that's exactly what you should have done. You focused on fundamental physics, and then about 2/3 of the way through the time, I made a note like, okay, like maybe we should also include some experimental. And then you suddenly said, okay, let's discuss your experimental setup, and then added a few insightful things there. I mean, it wasn't perfect, but I thought that was very well done.
I separated the point for the questions only. That was not as efficient as it may have been, but about the discussion I was very happy. And then the review we can have from 5 to 8. So should we start with 5? I think it's all connected.
Yeah. I mean, like a 5 is kind of the average point, and I thought it was a solid average review. I think it was a good summary of the discussion. But I think you punished the opposition too strongly, without really giving any better physics explanation for that. Right? So it was fine. Basically, I gave you kind of like fine marks all the way across, but there was nothing that was compelling. You didn't discuss any new physics. You didn't tell us concisely like what was missed or what were the points of contention why someone was right and someone was wrong. So it was okay, but for me there wasn't anything that would justify the higher mark.
I gave 6, so I was on the kind of same level. And for me, it was a big problem that you asked the questions, but you didn't want the answers. You just asked the question and didn't listen to what they're telling you. You just had them in the middle of the sentence. So we didn't learn much from the questions. Was too strict. Sorry, just one more point, and then I would say that you had a really easy job after the opponent shared. Like it was, I think, quite clear what was done, what wasn't done, and I did not think that you picked up on it, and it was a chance to, summarize it well. I think you criticized opponent for the point you tried to take. But do you think he's on the
So it will be 9 or maybe 10, but you better management.
Well, so I think in a fight like this, it doesn't surprise me that the reviewer scores and the opponent scores kind of match up. The folks that gave high reviewer scores also gave high opponent scores, or vice versa. And the reason for this, I think, is because the opponent was put in a very tough situation. You had a lot of knowledge about the subject, and you were kind of fighting tissue paper, right? Like there wasn't a lot of meat there for you to get in. However, the reason why I scored you well was that you had identified several aspects in your questioning that was directly related to their experiment that I don't think you cycled back to. You spent a lot of time on this theory. I thought you did a nice job of capturing that idea. The questions that you asked kept pushing back at some of the questions they had, injected and never gotten to. And then in your summary, I kind of agreed with your summary. So, I was stuck between this, it's like a 7.5, 7 or 8, and I rounded up. I could have just as easily rounded down. I thought you did a nice job.
Thank you very much, everybody.